With towering heaps of blasted rock as far as the eye could see, an army of workers was brought in. Their mission? Move 200 million tons of rock. Commanding giant earth movers, they demolished the landscape. Carting away hundreds of millions of tons of rubble. But all that material would not go to waste. It would soon be recycled as fill to turn the two small islands into a single larger one. But before that could happen, the sea floor needed to be cleared. For this task, a fleet of the world's largest underwater dredgers arrived on the scene. Like giant vacuum cleaners, their underwater hoses scoured the ocean bottom, removing a layer of soft mud 40 feet thick to expose the stable rock below. The cleared seabed provided a solid base for what was to come next. A layer of sand, followed by the pulverized remains of the island's mountains. With every truckload, the mile-and-a-half gap between the two small islands grew steadily smaller.
Everybody was under extraordinary time pressure. It was one of the world's biggest land-moving exercises in the history of the world.
Working day and night, inch by inch, workers on land and sea slowly turned two islands into one. By the time they finished, the workers had moved 600 million tons of earth, enough to fill the Roman Colosseum 200 times over. As the airport island was taking shape, construction crews had begun the daunting task of connecting the island to the city. Plans called for new tunnels, bridges, and highways to be built across 22 miles of land and water. Almost immediately, engineers ran into a problem: finding a way out of downtown across Victoria Harbor. Two automobile tunnels had already been built in the harbor decades earlier, but they were now overloaded with traffic, sometimes causing 2-hour traffic jams at rush hour. A third, much larger tunnel was needed. It had to be wide enough to carry 6 new lanes of traffic and long enough to span the 1-mile underwater crossing. Engineers devised a plan to assemble the tunnel underwater from mammoth concrete and steel sections. The sections were manufactured at a harborside quarry 10 miles from the final tunnel location. Each one weighed 35,000 tons when finished, as heavy as a fully loaded ocean liner. When a section was completed, builders capped both ends with watertight seals and then flooded the quarry. The massive tunnel sections were then floated out into the harbor. once at the final location, the seals were broken, flooding the section and causing it to sink. Powerful hydraulic jacks pulled the sections together and created a watertight seal. Then, builders made the final connections from the inside, and the tunnel was complete. It lay more than 50 feet underwater and stretched for more than a mile, connecting the busy island of Hong Kong to the mainland. With one waterway conquered, an even greater challenge loomed. Along the proposed route from downtown Hong Kong to the airport, there was another major body of water to cross. A 3-mile span from the mainland to North Lantau Island. Initially, planners hoped to build another underwater tunnel here to carry airport traffic. But the channel turned out to be too deep, and heavy shipping traffic at the surface would have made underwater construction far too dangerous. So engineers had to come up with another solution. It was as bold as it was breathtaking. They proposed not one, but 2 massive bridges, long enough to span the waterways and high enough to allow even the most gargantuan ships to pass underneath. The longer span, more than 1.5 miles long, would be one of the longest suspension bridges in the world. But it was a risky proposal. The bridge would need to withstand one of the most destructive forces on Earth: typhoons. Packing devastating winds up to 200 miles per hour. As many as 8 typhoons slam into Hong Kong each summer. Any bridge built here would have to first prove its strength. To understand how winds would affect the structure, engineers first created computer models. This model simulates the motion of the suspension bridge in a 40-mile-an-hour wind, amplified 1,000 times, allowing engineers to identify potential design flaws. Using the data collected, engineers next built a detailed scale model. They placed it in a high-speed wind tunnel and subjected it to a simulated Category 10 typhoon. The results were disturbing. The bridge would become dangerously unstable in high winds. Designers couldn't make the bridge any shorter, so they made it heavier. Below the main roadbed, they added a lower deck for trains and 2 more lanes for traffic. This design stiffened the bridge